Thank you. Yeah, thank you very much for coming despite all the incoming snow. We appreciate it. And today we talk about our carbons. You have seen these figures, these slides for a while. I want to say this is our first student CubeSat. So at the end, and also on common, our second. You have first, must have second, third, etc. So that's I'm the principal investigator for this one. I have a co-investigator, Professor Scott Payload, Dr. Sri Kanako, and Sri Kanako moved to the Goddard. And after we submit our proposal, but he had to give us some advice how to design the particle detectors. And also another thing is this is student project, but we had this led by the students, but advised, mentored by all those professionals, mostly from LASP engineering, LASP scientist, but also we had the mentor from the Loveland Repeater Association, Rob Strumby, and then Richard or REPTile were in the audience. Very appreciated, and they were with us from the beginning. And before even we proposed, their supporting letters still in the file, our successful proposal. They really helped us for ground station build, how you communicate with the CubeSat. And also another one mentioned, this is a consultant. He lives in Colorado Springs, Jim White. That's also those three outside of the LASP made a significant contribution to this project. And then students-wise, we have this led by those three PhD students. Lauren Blam is the audience, the project manager, and then David Gerhardt also in the audience, system engineering, starting from, David was this project from the beginning, or even before the beginning. He just successfully defended his thesis, which is based on this project about attitude control, past attitude. Successfully defended, he already won the job. Now he's been recruited by a local company, but he chose to go to Europe. They want to go to Europe, he found a job in Europe. And on the other one, people who work on this project, that's good on your resume as well. And also Quentin Schiller, he is instrument scientist, my PhD student, and they are still working on a PhD dissertation. Sometimes I refer those three students as the three pillars of our project, particularly to the end. That really stick with this project so far. Still on the. Just wonderful. They did a wonderful job. And then we talk about funded in 2010, and then we delivered about 2 years, and then launched on this day, and under this National Reconnaissance Office. This is a spy satellite. But they giving this CubeSat launch. They mounted to this upper stage right after the engine, and then somehow they assigned to NASA some slots, and then we got from NASA. So it's like good example of interagency collaboration. We have bad example as well, like MPOS, if you heard about. They didn't work very well. But this is a very good. They are funded by National Science Foundation and launched by NASA on the DoD satellite. And this is the orbit. And the orbit, I can tell you, we can guess the spy satellite. You're not supposed to know, but I can guess. The spy satellite is about a 780 circular orbit. So after they drop out the primary payload, they turn around, have the retro burn, so lower the perigee of our CubeSat. Because we have the requirement for our CubeSat, you're required to re-entry like within 25 years. The U.S. signed a treaty, the United Nations had a treaty. You're not supposed to have all this populated debris for a long time. So this one, so that's why the retro burn and then lower to the 480, and then that expecting the coming down within 20-25 years. That was my first slide. And also anytime, I really love you injecting your comments or questions anytime, and I would love to engage this discussion. Yeah, please. So for this one, we're talking about the CubeSat is this is National Science Foundation program, and they have a cap of 900K, and now including the launch. So I have the three requirements. One is advance the space weather and atmospheric related research. That's still called a science mission. And the second would be, say, you're training next generation of the space scientists and engineering. That also means you must involve students. That's required. Third one is you need to go through, meet this CubeSat standard. The reason is because for the facilitated launch, fund the launch. Those are three for the requirement. But also, I want to pause a little bit to think about, say, people in the audience, some of them have led all this, involved with the project, spaceflight project. 900K, what you can do, building a satellite. 900K, yeah, satellite is small, but you just reminding yourself, think about 900K, what you can do with this satellite. But then we proposed to have a CubeSat. Like in this next one, it's a little bit annoying. So we proposed our CubeSat, they have the core Colorado student space weather experiment, and we have our science objective, which is to improve our understanding of relationship between the solar energetic particles and also particle in the flare, and as well as the Earth's radiation by electron. So a brief introduction, say only this is Earth, like a different scale, and then the Earth, above the Earth, space is not a vacuum. They have this energetic electron and protons. They call radiation belt discovered by the first satellite, Explore 1, 58, and then Explore 3, and then later 58. So that was called violin belt. Violin, we can mention about violin. So there are charged particles trapped at Earth's magnetic field line. The white line shows like magnetic field line, Earth's magnetic field line. So they have charged population. Those are very dynamic. Those electrons and particular outer part, and then they go up and down. Then they have the intrinsic scientific questions: where they're coming from, how they be energized, and what causes the loss. They have all those intrinsic science questions. But also, either exposed to danger, exposed dangers like astronauts when they're going out for spacewalk. It also can cause the radiation damage on the satellite subsystem. So we have a real scientific reason, but also have the practical reason to understand those population better. So that's our science objective. But then, in order to achieve the science objective, then you need to make the science measurement. So the science measurement will be, say, the science requirement that we need to make the measurement. This measurement and to make those particles, this low Earth orbit, to make the measurement. That was symbolic features of our satellite, and then make the measurement in the low Earth orbit. So that's our science objective and science measurement. And also we emphasize this is a student project. Now here's a student, and then also keep in mind 900K what you can do to build a satellite. And then one way to do it is we have this graduate student project class. This graduate student project class, the Professor Payload, Scott Payload, also aerospace engineering department, and then we have this project class. And then the project class students come in to take the class credit. And they're not paid. Most of them not paid. They take the credit, they pay themselves for the tuition. They pay themselves for tuition, and then they come in, they work, and then they do as they learn as they do. That means they're real hands-on experiments. And one thing I want to emphasize, we can see almost everyone's teeth. They are all smiling. They're happy. They're happy. They are, they pay their tuition and come into this class, try to learn and to do. And this is a low-budget project. There's no way we can hire engineers to do the work all themselves. No way, no one can do that. And we have the student do it, and then but advised, mentored by the professional. Yeah, mentored by professional. The student will leading. And this is one picture, and then also another thing I'll keep in mind is you can think about this is like remember this one, because our student projects all by semesters. This is the end of semester. This is spring, end of the spring, 2010. Funding just came. Everyone's so happy and excited, and for the project, everyone's happy. And then only is one semester over, half the students are gone. We have a new student coming because you can see they didn't have that shirt. This is our student. Those new students didn't have this official shirt. So that's another thing I want to see people in the audience. You involve the project or lead from project. Can you imagine you in charge leading or involved big project, and the turnout rate is every 6 months half the people are gone, and then half new people coming. So how are you going to manage that one? This real startup, how are you going to manage? So the reason how can we do it is we are all emphasize what I can do here is, so I'm really make sure that students writing their final report, submitting their continuity document. One thing. Another thing is, which is like the student to manage it. We really say the students lead, and students, PMs and SE, they go and check. Every student sub-stimulate, they need to submit what they have been what they have done this semester. And then what I can do is I can hold in their grade. If they did not submit their final report, not satisfied, we do not give you a grade. right? And then we have to, sometimes we even negotiate, you need to do more, and I'll give you A, otherwise A minus. And it happened. And then the one student, he didn't want to do it. I said, well, if you don't do, I can tell you in the face, and you'll get A minus. You did a great job, but I want one more run. And then eventually he did it. He got an A. That's all I can hope. Not much. Yeah, they must remember one student. At that time, he really just stubborn. He didn't do it. So, well, I just tell you, flat, blankly. You get an A if you do one more run. Otherwise, record it. So that's all I can hope. And then that's another one. You can see this is. You can see this. Then the next semester, you can see more students come in, but also students left too. Just our big turnout. So that's all I can do is holding their continuity document or holding the final report for the grade. Another thing is this is not easy to go back and forth, but I still want to show. I want to see this is I found out after I started giving this talk. Look at the people's face, particularly if you can go to the previous one. Could do. You can see like the previous one, everyone's happy. You can see the face, everyone's smiling. And I want to show you the next one. Particularly if you look at my face, it's less smiling. We're still smiling. I'm still smiling, right? Still smiling less. But if you look next one, and then I couldn't smile anymore. That just if you look at this one. So that was not by coincidence. That's not by coincidence. That's we only had some picture taken. I look for, my goodness. If you look at more detail, even in Quentin, his smile was just. At that time, we have half a year to deliver our spacecraft. Our comm system not working at all. Our REPTile board, like the instrument board, not working. There's many things not working. That's the hardware. We have half year, 6 months to deliver. So music couldn't smile anymore. Yeah, that's the it really I just feel like funny, just couldn't spell anymore. But then I'll come back to this one. So this is the early one, and I want to show you here is this is the life size of the CubeSat. This is a 4-inch, and 12-inch in America, all 10 centimeter, 10 centimeter, 30 centimeter. So that was the life size. Now engineer prototype model. This lady hold Laura. Her name is Laura Bush, and then after she married, called Laura. What is it? Potter. Laura Potter to work in the LASP, and she was also the PM one time. And also the Quentin hold this one is actually our instrument, the only science instrument. And then science instrument is called Relativistic Electron and Proton Telescope, integrated little experiment. So that size is smaller than my fist. That one, that's where I make all the science measurement from that little instrument. And all the spacecraft designs certainly around that science instrument, because that's from science requirement. And also we mentioned about this this energetic electron and the protons measurement. And here you can see we designed, this is a server version of a design. We have the solid state detectors inside, and solid state detectors is just a particle come in, you can deposit energy on the detector, and then you can measure how much energy deposit, and then you can tell the electron or protons or how energetic those electrons are or how energetic the proton are. So and also they're surrounded by the tungsten, heavy metal, tungsten, and then aluminum, and just try to want to measure particles coming from the field of view, not coming from the side. You have to protecting, not reduce any contamination from the side or back. So that was our only scientific payload. So also we mentioned about before, there's this energetic electron and protons. That's energy interest we are. We also measure this kind of energy range, because the half MeV electron, half MeV, M here is like 10 to the 6, EV the electron volt. 1 electron volt means electrons going like a potential of the electric field, 1 volt. 1 electron go 1 volt, that means 1 electron volt. That's the energy you got. But this is like 10 to the 6 MeV electron. They were traveling about 0.99 speed of light. If you're going along the magnetic field line, that was 0.99 speed of light. It's very, very relativistic, very fast. It has penetration power as this 10 MeV. 10 MeV protons, they are heavy. They're not relativistic yet, but their penetration power is comparable. Like this one, they can go in through the space suit. That was one concern. This is like energy concern. That's also energy range we're going to try to measure. So I just have this intrinsic scientific reason we try to understand them, but also have the practical reasons. So this one for next slide would be shows the another picture show the reason we try to measure them is a story back a little bit. Even 2006, and I was co-investigator on this violent probes. 2006, we already found it. And when we designed the spacecraft, we knew the spacecraft in the equatorial region, and they can measure the most direction. But the problem is the electrons they going back and forth along the magnetic field lines, travel back. But they were not easy to distinguish how many electrons to precipitate into the atmosphere. They're not easy to distinguish from that. At that time, we knew also the existing SunPax, NASA satellite is going to re-enter. So that's why I had that initiative. So we tried to propose to launch a satellite at the low Earth orbit in conjunction to measure this electron population. Because this measures most population, but at this low Earth orbit, we can measure this precipitating electrons. You need to understand source and the loss. We mostly can do the precipitating loss measurement. So that was the, in that time, we had this idea and the plan to make the measurement. And also just say we have this conjunction measurement, we can better understand the trapped particles population, how the dynamic varies. And another one's here's because we just, now here, go Bronco. Go Bronco. But another thing that's about the same size, all on scale. This is all the size of spacecraft. I really put it on scale. I measured, actually the football is a little bit fatter than the CubeSat, but shorter. Yeah, shorter, yeah. That was the size of our satellite. So we make this conjunction measurement. And so that's here just trying to show the particles, electrons going along the magnetic field line up and down. But if you have measurement at the low Earth orbit, and you can better to understand the precipitating loss. Just one scientific reason, which the low Earth orbit helps. Yeah, and that's just another signature of our satellite, the illustrative of our satellite in the low Earth orbit to make measurement. And so now here we try to talk about, say, the whole satellite. And then our satellite is small, but they were just like a nominal satellite, just like a collection of the subsystem. A collection of subsystems. You can see any satellite have all those. Basically have all the subsystem. You always have the CNDH, command data handling. You have the power, EPS. You have the communication. Yeah, you have all this subsystem. And you have science payload. In our case, we only have one simple science payload, right? And also you have attitude control. But for us, when we just have this passive attitude control, just different attitude control. And we also have a passive thermal. Some satellites you have active thermal control, but we have all the passive, just because low budget, and we'll try to make it simple. And also we have some magnetometers are really for the housekeeping, for the diagnostics, and also help us to determine the orientation of the spacecraft, the attitude. So that's because low budget and also satellite, we really try to keep it as simple as possible, but as necessary. We try not to push the envelope, but also we follow through all the science requirement. That's another thing students really gain from this one, is the requirement. Everything starting from the requirement, you follow through the requirement. Anything outside the requirement, don't bother it. And I remember one time one student also coming to say, we have the data radius, like say, per 6 seconds. And then we collecting the data, takes like 10, we can take up like the 100,000 counts per second, but we in onboard processing, we only accumulate, say, we have resolutions only like 6 seconds. Sometimes students, why can't we do more? We can do much more higher time resolution. But if you do higher time resolution there, we need more calculation, but we cannot download the data. Just all this combined. It's not easy to, so we just say we run in the KISS mode, keep it simple. Some students want to do any fancy or no, just keep it simple as possible. Keep it simple, yeah. Yeah, and also another thing I want to show is just normally in Chinese we have always, I was born in China and I came to the US in '86. We always think that have the idiom said, I just say in Chinese and I translate it. The 麻雀虽小，五脏俱全. Let's say a sparrow even small that have a certain number of internal organs as ostrich. Yeah, let's say even satellites so small, but they still have all the other things. They still have all the subsystem. So for the other one, so that was the system diagram. Then I'll show you this one. This one shows the just like our mini version now. This is like latest version of the solid state version to show our satellite and also the different boards, how they arranged, and then our detectors, everything centered around the detector. Detector is also heaviest one, so that's we put in the center to meet the requirement of the center of the mass. Should not be far away from the actual center, right? So another thing I want to mention about the most expensive parts is about these detectors. And solid state detectors are $6,000 a piece. Or $6,000 a piece, and the rest of the thing I will show you in the end, they are not that expensive. The most expensive one, this one, $6,000 a piece. We couldn't afford many. We had a total, but we have this 4, but we had like 7 pieces, and some of them not working very well. We have no time to order more. Also, we cannot order anything at our choice. We can only buy. Do we have this on shelf? Because the lead time is so far away, we cannot just. So we originally we hope to have like 300 voltage bias voltage, but they only have this 330 left over from other big orders. So we just purchase those whatever is available. That's also we call everything we have in this project. We have called the all parts are COTS, commercial off the shelf. Commercial off the shelf, all from the shelf, and we cannot really say we want something specified, except our shirt. Student order it, design, and then we order it. That's the only thing we ordered. Yeah, everything else is really this. Whatever you available, we just purchase it. It's commercial off the shelf. Yeah, that was true. So this. But also before we had this one, diagram. I think that's something also we learned when LASP engineering really helped us for review. And then one engineer in Steve Stack one time, which we have this beautiful solid state drawing and showed, and then he said, without thorough analysis, whatever you're drawing is just a cartoon. You cannot just building satellite based on the cartoon. Now that's really etched on my head. So you have to do real thorough analysis. For example, that one we showed is really students have taken those finite element analysis, did those all the stress analysis, real analysis, so that design would pass any of the requirement, will all meet all the requirement. So after all this design simulation, based on that, before the cutting metals, that's another thing wonderful. After they did all the design, pass the review, and then start cut metal to. Now this is machined by the student as well. Yeah, right. But machines. This is done by the Nate. One student doing very well, and the last higher than him. Yeah. And also this one was a simulation-based design of detectors. This student my PhD student Drew Turner studied this with other student, but then Quentin picked it up. So another thing is we have to, because we want to make measurement or coming from a field view, so we have to say design how thick this is tungsten and aluminum and also titanium, how thick they should be. Yeah. So we have a student make all this run, very thoroughly run from shooting different angle, all different possibility to see reduce make the noise. We requirement noise signal noise ratio should be 2 or above. So I have done all this. This is like a version, many versions. Have done all the simulation until we feel comfortable. And then we start to cut metals and then do the to cut them to machine it. Yeah, this we have done all these designs. Again, all those labors, most of them are not paid. Students learn as they're doing this. So that was one of the reasons. Now this one start working now. So that's also for detector. Now this is like a detector chain, but simply saying you have the detectors, and then when you have charge particle come in, and then you deposit some energy, and then you have the charge amplifiers always amplify the signal, and then shaping them, and then depends on the energies energy, how high, how low this pulse. Then we can separate them electron from protons. And also we can separate the different energy range because you have like 3 or 4 detectors behind. So that was the energy chain. And then we have this called discriminator, and then we have the CPLD, do the calculation, binning, and then we send to the CNDH coil, and then send to the COM, and then send it out, send it back. So that was the just like our chain. Another things I would say, every satellite you always talk about what kind of attitude control, right? Attitude control. And for this case, we have attitude control. This is the most expensive one in kind of the high cost, performance, and then complex. The momentum wheel, then momentum wheel, gyro wheel, like all now Go satellites 3-axis stabilized. And most like if you have pointing requirement, then you need to have this momentum wheel, gyro wheel, and combined with magnetic torque. And so this is the most accurate one. For this one, if you requirement is not as much, say if you only 2 or 3 degree and a low Earth orbit, and you can use the magnetic torque, and then this is all active control. So for us, because we do not have actual pointing requirement, we are just the particles gyrating around magnetic field line. We do not have the requirement, so we just have this to call passive attitude. We don't have control. So what do? We put a permanent magnet on the spacecraft, and then the spacecraft try to align to the local magnetic field, and the wobbles overshoot. And then we put this hysteresis rod to damp that wobbles. After a while, you can stabilize. And this one, looks very, very simple. And say this one also only cost $1.99. And we bought a dozen of them with plastic bag, and they said do not swallow. Also they do and they'll keep away from children. So like have this warning size. This is $1.99 a piece. And this rod is like $15 a piece. Not expensive. However, when you design this one, again, how much this is coming from David Gerhardt's thesis. You can see how you design them, how the distance they should be put, what kind of magnitude of this magnetic field, how strong the magnet, and how strong the damping. All this one you have done all this detailed analysis. This is part of David's PhD thesis from this one. Yeah, looks very simple, $1.99 magnet, and put the hysteresis rod. You can go to wobble. Yeah, but lots of work has been put on. Yes, please.
What is the hysteresis rod?
Oh, hysteresis rods. This is called like they delay that reaction. Hysteresis rod is those ferromagnetic material. Is a ferromagnetic material. So when the satellites, like say you burned, and then they were kind of dragging you, just like damping them, and then when coming back, this always have a delayed response. So you without a hysteresis rods, and then you just continue always like bouncing back and forth. But if you have hysteresis rods, they convert that kind of momentum into heat. Yeah. So that slowly damping them after we are kicked out, and after like 2 weeks, now we start to stabilize. But we still wobble, but it's not that much. Like 20 degrees versus local magnetic field line. Yeah, sorry, the hysteresis rods, they were just dumping, converting this kinetic energy into the heat, so that just not to wobble too much, basically, drag you a little bit. Some people also doing like just put almost like put a ring of water. We can do a little bit. You just not jelly. Just don't do that fast. It's only a little bit slow direction. Thank you. I appreciate that question. Any questions? Appreciate it. Yes. Comments. Very good. So that's why I see a lot of work has been put in. Yeah, and then to design this, testing to do that. Yeah. Okay. So now, for all the different subsystems. The building students have different group building different subsystems, and then they testing them themselves subsystem. But then also the key part is like called interface between the different subsystem. So initially we had that called flat set. Just you put on the table, you have all the connecting supporting board. You try to do the called end-to-end test. That's the most tedious, but the most important. You have to communicate in between the subsystem, among the subsystem. And you can see also this one student was at which day we can do it. First time is all guaranteed, will not work. Second time also guaranteed. Guaranteed, just from experience, guaranteed. Anytime someone who say they had a project, they're going to do the end-to-end test together, guaranteed first time is not going to work. Second time not going to work. Third time not going to work. Guaranteed. This is like maybe like a version 7 or 10, but still not working yet. It's not working. That's because the student you building different subsystem, you have even though you have the specification requirement, but when you're building them, when you really run communicate, you find out you are missing something. Now you say you can do. So we have to done this always until everywhere is a green arrow. Everywhere green, and then we start to do like a fitting check, or also like parting them. Yeah. So, like for example, they passed one. When you pass all the check, also sometimes we back and forth. Physically fitting, put in this dimension, all the board. One put in the fit in, so without power first time, and then if it fit, okay, fine, without power, and put it back. Took them apart again, and then do the testing again. end-to-end check, and then put them back again. Sometimes when we put it back again, also first time we try power doesn't work. One time we found out our antenna connect as a cable. How do you run this small? That's very very narrow space. How you run the cable from the antenna to the CNDH, for example. And then the first time it wouldn't work, we tried to cut the board and then didn't work. So have to order that board. All those things happens. But when we had the fitting check and also power on, then everything worked. Then we started party. After all them passed end-to-end test, fitting check, power on, then partying them they're not going to move anymore. Not going to move, all being glued, not going to moving anymore. And that's part of what that means we're ready for final integration. And also here also the student, another thing for our project. The solar cell as a power, right? You have to put a solar cell on the space body-mounted solar cell to absorbing the sunlight, converting to the power. That's how we get our power. And the solar cell, each solar cell for me, but not for me. If you to purchase them, this is a triple junction high efficiency cell. That also costs quite some money. We couldn't afford it. That would cost at that time by $500 a piece. We couldn't afford it. But also fortunately, the DoD, Reconnaissance Office, they have a bunch of them. They bought like 10 years ago. But they couldn't use them all, and somehow they just donated to the NSF, National Science Foundation. And they have 10 years storage, and then we got some of them, and then some of them already oxidized, the brown colors, different colors. So I also have students pick up one by one, and then they do the testing. That's also student shows. The testing them, like for example, this one only partially working. There are forward bias current going through, and this one not working well, and those others working better. So they have to do all the testing. Each individual like pick one out or two or something to testing all of them. If performing not well, they don't use it. And after they pick up individual one, then they're mounting them to the solar panel. They do all the testing. Tedious work done all by students. Again, that's the only way we can do it. Student not paid who do this one, and they got a fantastic job. Our solar cell still working well. Like today, this afternoon, Laura just downloaded data. We still are downloading data tonight, just today. We're still operational, the spacecraft. The battery, solar cell all decayed. Another thing is, we mentioned solar cell, we didn't have any fiber, didn't have any glass cover. That was also debating whether it should have a glass cover. Some of the long-lasting solar cell should be, so like Go satellite, any operation one, they should have a glass cover. But that for us, our design life is like 3 months. So why you bother? Why you bother have a covered glass? Why you bother? Because only 3 months. So we didn't have any glass. So some of them may decay some, but so far depends on which panel facing the sun. Looks like we're still charging. Yeah, that's for solar cell. So this student did all this integration. Another thing I want very proudly to say: once they were integrated, parted, assembled, we never took them apart. Never opened again. That's something I feel like amazing. Yeah, never took them again. You never had any. Just once everything tested, put them together, never took them. One example is we talk about this RBSP. There are $700 million project, $700 million project, 2 of them, and then after they delivered to the Cape, Florida, one instrument team requested to take their instrument out. They already integrated, and that really pissed off all the rest of the PI. But that team said, well, the risk could be bigger if we're not taking that instrument out to fix it. But that just say that eventually they had to take that instrument out, and then they have done all retesting again, integrated testing, whole spacecraft. Like say 2 or 3 weeks, like months or so before launch, they have to take that out, and then fix that instrument, put it back, and then all the instrument everywhere has to retesting everything again. But our student made this one, we never need to. Yes?
Did you consider making a duplicate?
No money. That's the thing. Yeah, we would. See, for example, we couldn't afford. Like say the detectors, $6,000 a piece. We just couldn't buy like say triple of them. We have like some spare one has a flat set. We had a flat set, but not complete. For example, there's more detail after we launched, we did a recalibration of the data using our flat set. Or anytime we have initially we try to rule out our antenna is not working or so, we use our flat set. We almost duplicated, but not exactly. Yeah, we wish we could have that resources to say building 2. Some university they just maybe internally supported. They really building 2 identical copy. Yeah, they launched one. After a while, they found out it did not work well. Then they revised this one and then launched second one. Yeah, that happens. Yeah. Yes, Mike.
It looks like this is in a laboratory. It's not a clean room or bunny suit situation there, right?
Yeah, this one also, because our detectors are energetic party detectors, not like this optical, very. So we do not need to have any real clean room. Yeah, another clean room, but the electrostatics has to be followed. But not the clean room. We just say, try to make it, not make it messy, but we do not have this really. This is all done is the Department of Aerospace Engineering Science, that CubeSat lab. Yeah, that's CubeSat lab. That's really just depend on what measurement. If you sensitive measurement like remote sensing, optical, they will need no silicon or no stuff. So here shows that shows like we call stressful time. That was October. Sometime October, we're supposed to deliver December. Yeah, our comm system is not working. Our comm system is not working. Still at that time not working. In the summer, we show the picture that I couldn't smell anymore. That working. That time we decide to using the commercial available one. Before we even tried to design ourselves. Didn't work after 3 semesters. Then we decided, well, let's purchase the commercial one. When purchased commercial one, still not working. And then October, that's October. Remember, big snowy day. And then Jim White coming from the Colorado Spring, and then he stayed in a hotel because just too much travel, and then stayed 2 days, help us there. You can see people's face here. It's not like jubilant. And you can see Lauren eyes wide open, Yeah, it was stressful time. You can see everyone's face. Just not working. October already, we have 2 months to go to deliver. That's just intensive work, stressful time that time. Yeah, but after they test it out, and then this is the first call and plugs out test. After they made it work, this is November. One November day, we brought it out to this Davidson Mesa to do actual testing, communicating with ground station. Here I want to really say thank this Rob, Stribby, and then Rick. Kyle, they really helped us to design this ground station. We have no idea, what kind of ground station you should have. They really suggest, what you should have, what kind of radio you should have. And then we bought the radio, bought everything, and then we don't even know how to tune them, One time, remember during the review, then you went out, and then how do you setting them? And they really appreciate it for this help design and then get this ground station operating. But another thing we want to also thank this First IF in the Boulder, and they really graciously let us using their facility free of charge, because we need to determine the gain pattern. Because I have this monopole, and then we have this satellite, this skeleton. We need to determine the gain pattern. So which way satellite pointing, how much gain it is. Like for example, this is a node. Your satellite antenna should not be pointing this way to the Earth because it's a node, and this is the other end. But you have to understand the gain pattern to decide which way the antenna should be pointing down or should be pointing up. And eventually we decided you really should have been pointing down, pointing to the because the satellite was to try to align with local magnetic field line, and then even for the magnet have a 50-50 chance. Just put it one way or the other. 50% go round. If you go round, then the gain will be much less. And then Dave also even wrote a document to test step by step how they made sure the magnet put in the right polarity. Had a one whole document to say magnet put in polarity, correct polarity, and then you have to test it on the ground. Because if you put it the other way, antenna pointing up, then your gain is so much less, and you cannot get the data done. You communicate. Yeah. So another thing I want to emphasize: this one's on the roof of the other building, and another thing I want to say a little bit. You can think it's about bragging, but bragging say, LASP, we are first of all doing the fantastic mission operation, and Bill Parcel, director of the mission operation, fantastic operating all the Keplers, many satellite. LASP also do pretty efficiently. They have also student trained and doing that. But then I want here on the top of that, this student we have directly talking to our satellite. Yeah, mostly the LASP doing, they have other satellite, they have other dish collecting the data, and the LASP is doing all the control. But here the students were directly talking to the satellite, do the control. Like for example, today, Lauren just sent a command to say dump more data. If when the voltage is high enough, just directly talk to the spacecraft. That's just doing that, very amazing. It just me still wonder. I didn't do it, I'm a student again. This is just amazing. With the mentor, how you build this spacecraft, what frequency to use, what radio to use, what all those TNC to use. It's just wonderful. Another thing is we also talking to when we purchased this satellite, even before launch, we had a high wind, and then the antenna just one day while I was riding the bike on the background, I was blew away, and I was radio blew over to the ditches. And the first thing I care is not care about my. First thing I look at up at the antenna. I'm telling you, first thing I will come up look at the antenna. Oh my goodness, boulder, famous, well known for the highway. And then originally, before even satellite launched, the bracket, broke. The OEM broke, and that was aluminum. But another thing, this I made the example to all the students. When it broke, who cares? No big deal. We just made the stainless steel. The point is, anything here broke, we can rebuild it. But once you launch a satellite, if something wrong, then you're out of control, out of luck. So this one, we had all stainless steel, the bracket. We made our student, but that student would pay like $10 an hour or some undergraduate. He just went over the machine shop and got this stainless steel, replace this one. That's just one point to say. No, on the ground, you can, that's the difference. Spacecraft design or spacecraft build, and then ground, you can fix it, but then once you launch, it's different. Another thing I want to mention, this is funny, this is really, we bought this yellow Margankin stunning tape, measure tape. Then students roll them and then tie with a fishing line, and then 5 fishing line. And when the fishing line go or cross the like a resistor, and the resistor have the current sending over, you want to deploy the resistor getting hot, and then cut fishing line, and then deploy the antenna. And that was another amazing thing here. It still shows here's the antenna was rolling outside, inside, and this is a fishing line, and then the tie, and then when you see the antenna, how they deploy it. Yeah, they deploy it, and they will have tested many times. Again, many times. Many times. So that was in the Davis Mesa. Davis Mesa, they had this testing, and everything worked fine. Seems to be working just fine when we launched. And also they had requirement we cannot deploy antenna at least like say 45 minutes or after you kick it out, because they do not want to have any interference with the primary payload. Yeah, we have to show the circuit design, so you're not going to deploy antenna right after you'll be kicked out. Yeah, all those requirements to be met. Now after the plug out tests, and then we sent to this the postgraduate school, Navy Project Monterey for vibration test. This is Dave and this is Ian, and you can see the high five after the test. After also vibration is did the performance test now, and the first order come over just shake, no noise. But then did all the performance tests, everything's fine. They start high five. I'm going to tell you another CubeSat we are on launch together when the after vibration in there, and then coming back when shake, they have clunk, because they forgot to take out the guiding pin. They had 2 guiding pins when they latch them. 2 guiding pins, they forgot taking them out. After the vibration, the guiding pin came out. So they have to send a team over. For that one, they just took it back and then open up and then take those guiding pin out. And after that one, we come back for the thermal vac. That's also thoroughly thermal vac. This is on the LASP, the vacuum chamber, and thermal vac. This is also like one of the first at the LASP, because we have a whole satellite. Also, we communicate ourselves. We want to. So this satellite is inside. Here with this ceramic chamber, and we have little concern. Was like say this. This reflection from this metal chamber might have slight chance to damage our radio system. So we have to put this antenna, this is a yellow tape, and inside this is a ceramic chamber. So have a reduced echo reflection. So the ground station, this is this cable, and then this antenna coming out of the spacecraft deploy, and then the ceramic chamber student made the order, and they came back when they found it a little short, so I have to bend this now bend this antenna a little bit. You tape them, bend them, box them up. So they've been talking for like many days. It's really simulating in a space. Simulating space. So you can see that we have the temperature going up and down for many days. And the students at that time takes like a 4 hours shift, 8 hour shift. They've done like 8 days. Cycle up and down, really live in the environment, try to live in the real environment. So even though we can talk about all this student project, so much effort you can see we put on there. What I'm talking about is only on the high level. If you want to go detail, just many talks. And our students, like I say, they were a short of student. We got a new student now. Jim Mason also. Now from the next, now I'm going to show you next generation of CubeSat, also participating. Our other students just help out 4 hours, 8 hours, and also from the thermovac test, they're boring better. Then that's just very good news. Hoping nothing happens. You're just sitting there for 4 hours, 8 hours, nothing happens best. Boring is best. So we're very boring. That is all boring. But one day I remember while teaching, they continue teaching graduate student class. I went to the classroom. Jim was sleeping on the couch on the classroom. So what do you do? He just finished his shift, helping us doing this, and then he was. Just went to the class directly 9 o'clock, but a little bit earlier, sleeping on the couch. And just all students did those things. Yeah, and then the student also they had so much time somehow. This is our detector. One student, Nate Shako, that he just asking, hey, we want to carve people's name on that spacecraft. That's also one to encourage students say, well. You can tell your children or your grandchildren, so you have satellites, flying and da. And then he carved, he so accurately laser grave in all these names. He asked at that time, that was before even we delivered, and then say, whoever contributed was a name. Now we can see here the Rick, Richard, Kyle, and Bob Trainway, and all here. And then that was before. And then later on, we also have other people who didn't get a chance to carve them. They produce more review, just like say. Help, all the help. Another thing you can tell, even we call the student project, and then we involve about 65 of them, but people here is way more than 60, double and triple, and that's who really helped. Mentally, this is all for this project. So now this shows that this day system engineer delivered before the final launch. Deliver, and this is the P-pod put on. Now this different team now. This team, they are supporting the launch. So all mounting this one, this after Balkan cabin. So the mounting the total, we have like 11 CubeSat. 11 CubeSat. There are some of like 1 unit or 2 unit. Then this is the upper stage. You can look how big the upper stage are. All these 11 CubeSat, little tiny thing put there. Upper stage, and then they were. For the launch, still that's little thing. To have 11 CubeSat there.
This was Vandenberg.
Vandenberg, yeah, California Vandenberg, yeah, very foggy, yeah. So after the launch, you can see the primary payload deployed. That's a jettison on the first 8. Now this primary payload deployed, and then this one turn around and had to retroburn to reduce the perigee. They turn around, retroburn. Then they kick out all different CubeSat, and ours like third one come out. Yeah, this CS Colorado students been space weather experiment. So that was the launch, and so we launched on this day, and then we received the beacon on the first pass over the boulder. That's also the comforter side. But then, depending on waiting, this is already successful, and then we commissioning phase on the October 4th. That was also a special day. I didn't know that time. And then we have data that really far exceeding expectation. So for me, before I see the science data, I did not smile really from the heart, because by me, the mission is still called science mission. Student involvement, big achievement education, big achievement engineering, but I really still want to see the science data, publishable science, high caliber science data. And then before I show you science data, we have also just show you the attitude control. Now, we don't have attitude, passive attitude control. We do not have any pointing requirement, but we only have, need to have the knowledge which pointing. So we have another magnetometers on board, Magnetometers also very cheap one because $3.49, like Dave showed me that spreadsheet purchased from Digital Key, $3.49. We do not need to have accurate measurement about the magnitude. We only need to know the component, vector component. So help us to tell us when the relative angle between the satellite and also the local magnetic field line. That's what we need to know. We don't have that requirement to which we pointed. So $3.49, that worked well. Yes, then it tell us three components, and then can give us the information, say how well they perform. And that's also part of the thesis. If you combine with, like, say, this, we also have a full body, have the temperature sensor, photo sensor, and then we have the magnetometer. If you combine this, then we can determine very well the satellites at any given time, their relative position. Yeah, but after a while, our solar sensor burned out, and then temperature sensor helps them, so we have less accurate determinations in which we're pointing. But again, this is not really a requirement. That's a key. Yeah, we do not have to read. And also knowledge is what to determine what analysis you need to do, how accurate you need to know the knowledge. Yeah, with all the solar sensor, temperature sensor, magnetometer, then we can have very accurate determination for that time period. So then we had our first detector turn on. We turned on October 4th, 2012. Yeah, after like less than a month commissioning, we turned on the first detector, and then we turned on the second detector. And I just after we turned on the detector, after I saw this one, I mean, couldn't imagine them. I just happy, and then we're happy. And that's the time I was really happy. Had this celebration already. And also I'm telling you, 1 year after that, we're still taking the science data. We have another celebration, and also want to make it clear, no project fund used to buy beer. I buy from my own pocket. My pocket. But happy to show. You see, we had a celebration that day, and then 1 year later, we have celebration part of the team and also new team member. We had another celebration. Just happy, so happy. Lauren, small size, she holding a big jar of beer. Now I'm a small beer. Anyway, we're happy. I'm happy. Again, this is just good. So now you show this is like a general shows that our measurement is like we're not going to detail the scientific first channel and the second channel and the third channel, and the measurement was shows consistent with some magnetic storm. During the magnetic storm time, the enhancement occurred, and then during the enhancement occurred, and during the quiet time, it slowly died down a little bit. And also we had the first anomaly already after like 10 days on orbit, but luckily we believe some light trap. And another thing, we could not afford those light trap free or red hardened parts, but that luckily they came back. Light trap did not did not stay there. They came back, and then we burned some ADC, some sensor, but we're still operating. And then again, now I'm going to compare some measurement from the Violin probe with our measurement here. And you can see some similarity. You don't need to go detail, but I want to show you. So the similarity you can see before the storm, this is called slot region. You can look at this shape. This shape is so much similar. And during the storm, the enhancement occurred. And you can see the detailed shape, and we have all the measurement. And later this instrument, another enhancement here, but this one has a much finer energy resolution, so they decayed faster, and our case didn't decay that much. But we have all this detailed measurement, also the penetrating inward, we call the some transient rain, and we have just all this detailed comparison. That was just even our community, not just our team, just all, really we say that in the same par as the Violin probes. This is a $700 million project. They have much higher energy resolution. We did not have that high resolution, but our measurement just good, just good. And also, this is from our own measurement only. We have a proton. Here's a proton. Here's the electrons. That also can give the near Earth environment. In this kind of presentation, what is energetic particle environment in the near Earth? Yeah, this is called South Atlantic anomaly. South Atlantic anomaly that just have a much weaker magnetic field, a lot of trapped particles precipitating there. And this is outer belt called electron outer belt, and then this is a high energy electron. But the proton, we don't have solar proton event during this time. We didn't see solar proton high latitude, but we only see this trapped inner belt region. Just very, very clean. Only for the people seeing this one, this is from our little tiny spacecraft, and they were impressed. Yeah, me too. I'm still impressed, you see. So that's now for the first few months measurement, we shows, and the first one, we already have published paper, and published paper, and then we have this several event. We have working on this data in conjunction with the Van Allen probes, in conjunction with others. But this is from data. There's several public. In total, we have 11. Total have about 11 engineering paper and a science paper, peer reviewed. Yeah, published from this project already. Yeah, so that's the one thing maybe I can mention. This one is one we also, the Laurent Blanc, the first author on this GIL, came out last year, and it shows has a balloon in the Antarctic, and this part of the Van Allen probe mission opportunity. That balloon is Antarctic, and then we can measure this conjunction with this balloon, and then we have conjunction with Van Allen probe as well. That paper was published already, and other papers as well. And also to mention about then later on, we have satellite went silent on March 8th, and that was also interesting things, because after we give this talk, people in the LASP are asking how long the CubeSat will last. The minimum mission is 1 month, and then full success is 3 months science data. But we already passed that, but then completely went silent for many months. So before that, when we had Quentin, the student, people keep asking, say, how long it will last? Then he just challenged people, you can make a bet, $5 per person. You just name one day. Name one day, say when the satellite stopped sending scientific data back. And then they all had, I think Bill Peterson had a bet 2 days or something, $5 a day, and then Bill Peterson got $10. And then one time, when we went silent, then Bill Peterson's guess was closest to that day. At the time, we said, okay, now we had about total $80 something, 80 something. Now we have 16 bets. And so now we say, okay, Bill can take this $80 to buy us a drink, for us. And Bill said, what a deal, I have to spend more money? It's only $80 and I have to buy all the team a drink. But then Bill is very, very graciously holding a big party in his house. Julie, thank you very much. Hold party for the team and for other colleagues. But before that one, I was talking about so he was closest one. But then another thing I want to mention is another thing is I think really our SE, Dave had this tremendous contributions, because initially we had to man the pass. Students get up 1 o'clock in the morning, 3 o'clock in the morning, wherever they come to try to man the pass. Yeah, and then it's so tiring. I can see my student Lauren, Quentin, everyone said, we cannot do this continued. But then during the primary mission, we didn't want to try things new. Did a little bit there, so we try to still man the pass. But later on, after the primary mission, and they mostly did this autonomous. Made all the script autonomous. So the antenna just tracking based on this TLE, two-line elements. They know where the satellite, and the sat PC, and then tracking the satellite. So they know where the satellite comes, and then they automatically tracking, our antenna automatically tracking that. So we went silent, and then because it's autonomously done now, so we continued the tracking it. And after 2 months, was all, should we give up, because that costs you a penny, just keep tracking them, we keep tracking them. We already done the end of mission review. We have even done the mission. We have done 4 tree, just try to analyze what was going on, what caused that failure. But then they suddenly, on the June, and we started to hear the beacon again. We heard the beacon again. And heard the beacon again, then we gradually established bi-directional communication, and everything seems to be fine. And then we download the house beacon data, and then we started to take science data again. So that one, most likely the reasons from the air log, the comm system was stuck. We have 2 processors. The CNDH have 1 processor, and the comm system have processor. We only have the software reset. If the comm doesn't hear, if the CNDH doesn't hear the comm for certain hours, the comm will reset the CNDH reset, CNDH master, CNDH reset comm. But we do not have the hardware resetting. We do not have that, just shut the power off. We did not have that part. Just try the software reset. So when the air log came down, they just said the comm doesn't respond, comm doesn't respond. CNDH came, our satellite is still taking data, but the comm was stuck. They could not reset it. So after a while, they also draw a little more current. After a while, the battery drained, completely drained. and the whole thing reset, and then came back. This also is by the everything came back, calm came back, CNDs came back, and then just starting from beginning, just like beginning after we launched with a dead battery, just seems like that. You after completely drain, everything reset. Just almost like you have a PC or Mac, you something was stuck, you cannot do much. You just unpower, reboot it. The whole thing, everything came back. Everything came back. Lucky, now everything came back. So that one is the calm was stuck for so long until the battery completely drained, then full reset of the spacecraft. So after that one, we continue taking. We have taking like 3 months vacation this spacecraft, and then we continue making the measurement. Continue have the analysis. Now we continue going on all different feature of this energetic particle electrons, energetic electrons. So we continue on. So our last data we're taking is January 4th. We just download today. And another thing is because battery is really degraded now, I have to say. Battery we never even wild dream, we never imagine this would last so long. Yeah, battery. They have a certain cycle, charging and recharging, depletion. We never imagine that so long. And really past all our wildest dream or expectancy. So right now we depend on the solar beta angle, how much is exposed to the sun. And if you have long eclipse, the battery cannot stay. So we cannot really take in the sun's data for long. And also depend on which side, or looks like which side of solar panel. Some sides will have 8 cells, some sides have 6 cells. But just as it's aging, we don't know which side. Sometimes we just seem like right now they somehow we have better charged, and then we can take data, we can download the data. But other time, depending on the beta angle, we just in a hibernation mode or just like safe mode, this beacon. So still working, but not like full capacity, by far not full capacity. So, but again, the good thing is we are all automatic now. So you will still tracking them automatically, but sometimes we have a manned path to send different command. They are still respond. So that's what I'm trying to say. So that's my conclusion for our first satellite. And then you can see this one was our tiny, this is CubeSat has been operating for over a year. Way past the expected one. 1 month minimum, 3 months full success. And we said this is all success for education, engineering, and science. That's really a proof we can do that. We are low budget with the students' involvement, with the mentorship, we can get the one done. And then we have all the science results done. And also we're talking about our data now also archived in NASA website. And then again, we say we are really same part as other NASA satellite as well. Our data is being used by us, also other people can use that as well. Archived in the NASA website. And we have total about today, as of today, we have 11 peer-reviewed paper published or in press. Yeah, for this project. And then that's also going to show Glaming, that's like Quentin's not just only instrument scientist, also he's doing the chief financial officer job. That's, you can see, so I have an idea of the breakdown the parts, the cost. Yeah, cost. The most expensive one is this REPTile, means this is solid state detector, $6,000 a piece. And all this, you can break down the different subsystem. But overall, still, about 85 or 90% cost is for the labor. The labors for the student, they're not paid for the first 2 semesters, we're taking the credit. But after that, the student will continue working with us. Then we start to pay them like summer, we pay them. And also after 2 semesters, they working like hourly paid. And also some student like Dave was system engineering through this out, and he's paid as a research graduate student, research assistant. So most part is still labor. If you're talking about NASA's satellite, 95% normally is labor. 5% is the parts. For us, the parts is about 10 or 15% for this one. So quickly I'll go through, have 3-5 minutes, just our next generation. Our next generation, this is led by Tom Woods. He's a PI, principal investigator, the associate director for engineering, our lab. He's going to do the this is a 3-axis stabilized satellite for the solar physics study. That was called MINX. And so that's now with different team now. We have this again. This is a spring of last year, 2013. This is Tom Woods, and then we'll continue running this graduate student project class. There's a student, some of the mentor. This also the CASB mentor, and the Scott Payload professor again we together still run this class. And I can show you now we have also our official shirts too. Ordered. Now, people who without shirts, those are mostly the mentor. experimentally. We are continue running the graduate student project class. This is our next generation. We have a lot of heritage now. For example, we're going to use the same ground station. We're going to try to use the communication system. We're trying to use the similar revised EPS. But this one, the real biggest challenge for this one, this is going to measure the sun. That require you have a pointing. That require you pointing the sun to a certain degree, like 0.2 degree or better. So that one you need to have a star tracker, have this the active momentum well talk about this called attitude control. For that part, we could not build that one. We like to purchase commercially, try to purchase for local company, Blue Canyon Technology. They are going to supply this to us, and this project is partially funded now. Partially funded, not full scale, not full throttle, but we are expecting eventually going to full funded. We can launch this one as well. But because the complication here is because you have to point to the sun, you require more power. You have to deploy a solar panel. All those things got more. This is called next generation of CubeSat. That really have the much more sophisticated attitude control. Before we don't have any control, just magnet. Yeah, that's for our next one, because I mentioned the first one. This is my last slide. But thank you very much. I'm very happy to entertain any questions and comments. Okay, thank you. Yeah.